SwayamPrabha. Digital India. Educated India.
So, before you start this lecture, let us have a little bit recap of what I told you in the last lecture. So, we have been discussing about massive transformations. Massive transformation is actually a diffusion less transformation, and in which the one of the solution phase at high temperature transformed via nucleation and thermal mediated growth to another solution phase without any change of composition. And this is predominantly observed in copper based alloys like copper aluminum, copper zinc, copper gallium, and many other alloys like iron carbon, iron nickel, and other alloys, iron cobalt. And this happens mainly by formation of these product phase at the gain boundaries of the parent phase incoherently nucleating and growing with the incoherent interface with the product phase, with the parent phase. So, this is what we have discussed, and I showed you a few examples that how the product phase, which is always defined as a with a super subscript m to make it different from the equilibrium product. Equilibrium product will be always alpha, that is why we make it with a different symbol alpha m, and this grows into the parent into the product phase, in the parent phase with the irregular morphology. This is an important characteristics of these transformations. Now, let us I just showed you that how the driving force can be generated by quenching the sample of the alloy through these different temperature series. Now, let us take an example of copper zinc, which I also showed you, and this is available in the book by Prof. Sterling. As you see here temperatures are not T1, T2, T3, T4, but specific values are given, and this is the part of the copper zinc phase diagram, and we are talking about an alloy which is a I think 38.7% of the zinc, and here all the temperatures are shown. The T0, which tells you the temperature corresponding to same P and G values of the beta and alpha are shown. Along with that, martensitic star transformation temperature is also shown. You can clearly see this is MS. So, that means what? If we quench this alloy to make you assured that how things happens, if I quench this alloy from 850 degrees Celsius temperature to 400, this will lead to kind of a massive alpha formation. But if it is rapidly quenched, rapidly means very fast quench from 850 to minus 100 or actually below 0 degrees Celsius, then only martensites will form. So, martensites are also observed in these alloys. Therefore, to study these alloys we need to be very careful to study the massive transformation of these alloys. Now, T0 is something like that, it passes to almost center of these alpha plus beta phase field. This is alpha plus beta, remember, and so this is told T0 corresponding to beta to alpha transformations. So, it is very clear that only when it is cooled down, the alloy is cooled down below T0, because above T0 beta will be always favored, beta will have a lower free energy than alpha. At T0 alpha and beta will have the same free energies, below T0 will have alpha will have lower free energies alpha beta, but that means what? Massive transformation driving force will start being available only when it is cooled below T0. Let us see how it can be explained. At 850 degrees Celsius temperature, the free energy curves of alpha and beta are drawn, you can see that, and the common tangent is this. So, therefore, this is my alloy composition 38.7% of zinc, and therefore, these alloy there is no driving force for the transformations of the beta to alpha, as you clearly see, although it should be mixed together 850 somewhere there here, okay, as you clearly see that there is no driving force. So, there is no point in drawing common tangent also. What happens at 700 Celsius temperature? 700 is somewhere there. So, 700 Celsius temperature is below T0, correspond to this alloy composition of that, okay, and it is almost actually close to T0, that is what is shown in this diagram. So, the alpha and beta, and this is a common tangent, and this is this point which correspond to your correspond to the equivalent free energy values. So, for we can clearly say that at 0.38% of zinc, it is T0 is actually 700 degrees Celsius temperature. So, what happens if you cool below T0? Then only things will start happening, right? So, as you see here, this is what you must focus very carefully. As you see here, this is the alpha, this is the beta free energy curves. Now, I can tell you that this is this precipitation. So, therefore, I draw a common tangent between them. So, if I do a common tangent, this is my free energy for the mixture of alpha and beta. That is what is written. The difference between this point and this point on the common tangent will give you delta G precipitation. Delta G precipitation means delta G alpha plus beta, right, because alpha will precipitate out from the beta. That is why it is called precipitation, and that precipitation will happen like a Widmer-Stratton morphology. So, that is the driving force. Now, for the massive means there will be no change of composition. Remember, precipitation will lead to, this is the alpha composition, this is the beta composition. So, alloy composition was these. So, that is will lead to separation of the or the distribution of the elements between alpha and beta. Alpha will be rich in copper, beta will be rich in zinc. Now, massive transformation means without change of any composition. So, therefore, directly from this point to this point, beta to alpha. So, that is why this is the massive transformation driving force. Here is very evident the massive transformation driving force is slightly lower than the precipitation driving force. Now, if you go down to 500 degrees Celsius temperature, as you clearly see, massive transformation driving force and driving force for the precipitation is same. These are all same. There is no difference, and this is delta G massive. So, that means what? As you go down the temperature, massive transformation driving force slowly will increase. Although at high temperature it will be little bit lower than the precipitation, but then it will compete with precipitation process, and finally it will win over. And also you have to understand, even if the driving force of the precipitation and the massive are little bit different, massive transformation driving force is lower than the precipitation driving force, the chances of massive transformation happening in the system will be higher. Why? Because massive transformation only requires thermal migration of the interface. There is no diffusional change is required. So, that is much easy, that is the time required for transformation will be much lower. So, that is why even if this delta G precipitation is higher than the delta G massive transformation 600 degrees Celsius temperature, the massive transformation will prevalently happen in these alloy systems. So, I hope these constructions are very clear to you, and this must be clear to you because this is a basis for the understanding of phase diagrams and the phase transformation G versus compositional diagrams. We can explain the driving forces available for that very easily. As I said clearly, in these alloys the nucleation, actually that is what even the book by Jena Chaturbedi writes very clearly. If you clearly read it properly, I will read out those sentences. It says the growth of the nuclei of the massive transformation product involves transfer of the atom across the boundary between the product, the parent and the product phase. The boundary is capable of migrating through the gain boundaries of the parent phase, and also no definite crystallographic oriented relationship between the parent and the product phase is found. Therefore, interface between the massive phase and the parent phase is thought to be incoherent. People have proved also by experimental the interface is basically incoherent, that is why it can move so fast. This is the main reason for that. So, as you know that massive and the Martini transformations are distinctly different from each other now, but they do also compete at lower temperatures. So, Martini transformation is a diffusionless military transformations. It is not a like it happens because of the shear of the along the Giselle interfaces. Now, here the growth of the product phase is basically happening because of thermal activation. That is why it is different, distinctly different from Martini transformation. As you know, these two transformations compete to each other. So, therefore, we can actually generate something what is known as TTT diagram for massive and the other transformation, and this requires little bit discussions. And as you clearly see here, this is temperature, this is time, TTT curve which I have introduced for the steels already. So, these are the different cooling rates 1, 2, 3, 4, okay. 1 is slowest and 4 is the fastest, and these are the actually C curves. For the precipitation massive, martensite will not have any C curves because it is not a, it is a military transformations, and therefore it's the fact that it shows, I have been telling you again and again, massive transformation has a nose curve because this involves nucleation on growth also of the interface. So it has a little bit of diffusion involved, which is maybe thermal diffusion, but may not be chemical diffusion, but involves certain diffusions which cannot be ignored, although this is not clearly understood so far, but one cannot refute that part, refute that thing. So as you see here, precipitation will require slower cooling rate because that's require compositional partitioning. Therefore, if we cool it slowly by 1 or 2, the precipitation will happen. This is the C curve 0%, 50% for the precipitation, and then if you cool intermediately, that is what the 3 is shown. The intermediate cooling will lead to certain kind of a massive transformation. It will bypass the precipitation. That is what we have seen in the earlier pictures also. It will bypass the precipitation and lead to the massive transformations, and massive transformations also depends on, it will not happen all of a sudden, although I am saying it will happen at a very high speed, but this thermal migration of the atoms or the interface requires certain time. So still this time scale required is much lower than the precipitation. Okay, you can clearly see that this is the time difference from these to these, this is, and this is the time difference these to these. So that is much larger in precipitation than in massive. And martensite does not require any time, it is a thermal transformation. So you simply quench it below MS temperature, it will transform by a shear process to martensites. That happens. All these transformation can compete each other in the interfaces, like here between 2, 3 and 4 and 3, if cooling rate is somewhat there, it can compete each other. What can happen is that between this temperature to this temperature, where somewhere there here, okay, it will massively transform, and then whatever will left parent phase, that will transform to a martensites. Similarly, thing can happen like that also here. Okay, you can see here initially precipitation will happen, and then it will go, and then once this is crossover, then whatever beta will remain parent phase of that composition can transform to a massive product. So we can actually draw such a kind of a time temperature transformation curves for massive and the precipitation as well as martensite transformation. Is very clear that it is possible to do that for all the alloys, and this is actually helpful because in many cases we do not want the martensites, because martensites will have a lot of strain inside it. Why? Because this is shear transformation, it happens along the glycerol interfaces of the parent and the product by twinning or dislocation motions. So this will lead to a lot of stress in the product phase, and we want to avoid that. So but we want to also transform, we want to also have a product which will be which can be retained at room temperature. So massive is this is alternative people have found. So depending on the alloy compositions, we can actually choose the pathways for these transformations. That is possible. So let us stop it here. I think okay, this is again shown similar thing depending on the cooling rates. This is actually taken from the steel, this is not from the copper alloys. As you see here, that as if you cool it slowly, you have orientation, nucleation and growth, that is precipitation, and then if you cool it a little fast, you have a massive, and then you have a cooling very fast, a much lower temperature, you can have a very fast cooling lead to martensite transformations. And there is a region which is placed basically in between martensites, massive and martensites, so one can actually access that also. So remember, massive transformation leads to incoherent interfaces, martensites leads to sometimes, many times there is a specific orientation relationship between the product and the parent phase, because the shear movement of the atoms, because of the shear forces, the certain planes needs to be kept undistorted, that we have discussed in the last class also. So with this, let us stop it here, and basically I am going to start again a new transformation in the next class, that is from order disorder transformations. That also requires diffusion, unlike massive and martensites, but different types of diffusion. We will see it in the next lecture.